Alright everyone, so in this video, we're going to be wanting to solve for I1, I2, and I3 of this circuit. And the way we're going to be doing that is by using the junction rule, the loop rule, Kirchhoff's law, and all that sorts of stuff. So yeah, let's just get right into it. So before we approach this problem, because we have three unknowns, that's a pretty good indicator that we're going to need three equations. One of those of which is going to be the junction rule, and two of those we're going to be using the loop rule to obtain those equations. So sorry, just looking for one of my markers. So yeah, let's just start off by drawing the equations when we use the loop rule. So let's just take a look at what we can do. So here, this is just going to be a random loop that I draw. So what I'm going to do is I'm going to be taking this loop here. So we're going to be going from A to F to E to B and then back to A. So let's just write out the equation for that real quick. So by the loop rule, we know one side of our equation is going to be equal to 0. That's always the case. And now let's look at the direction that we're going in. So here we're starting at A, then we're going to F. Now we're already encountering two different things. We have this battery and this 12 ohm resistor. Now for the battery, it's pretty crystal clear. When we go from positive potential to negative, when we go to positive to negative, that always means that it's going to be a negative 18 volts. However, for the resistor, it's a different scenario. So when we're doing resistors, we want to look at the direction of the current. So here we can see I1 from the top of the loop here. It's going to the right, but if we were to draw, sorry, I'm looking for another marker. If we were to draw the direction of the current for I1 as it goes around this loop, or at least this part of the loop, we can see that as we go from A to F, we can see that we're opposing the current. So here, the current is going upwards while we are traveling downwards as an observer. So when we're opposing the direction of current, that means that the potential across this 12 ohm resistor is going to be positive. So it's always going to be the case that when we're opposing the current, it's always going to be positive. And we know potential is just resistance times current. Here we know we're given that it's 12 ohms. So we have 12. And the current going across this resistor is just the I1. So bam. Actually, I'm going to write that a bit better. So we have plus 12I1. And so yeah, we just keep going with our loop. So from F to E, we have nothing there. And when we go to E to B, now we have this 6 ohm resistor, but now this time we have current I3 traveling across this line right here. Now in this case, we can see that as we're going from E to B, we're traveling with the current. We're traveling with I3. So when we're traveling with, that means that the potential across this 6 ohm resistor is going to be negative. So we have negative, and we know the potential is just resistance times current. So we have 6 ohms. So we're going to write out that 6, and the current I3. So bam, now we have that. And now going from B to A, we have nothing there. And just like that, we have our first equation. Now for our second equation, what I like to do is get the loop around the entire thing. So let's just take a look at that one right now. I'm just going to erase these lines really quick. And now this time, we're going from A to F to E, D, C, B, A. Now for our equation, we're always going to have a 0 on one side. And now, since we're traveling along the same path, so at the start, so from here to here, the equation is going to look more or less similar to the first one at the very start. So we have minus 18 volts plus 12I1. And then going from F to E, there's nothing there. And now this time we're going from E to D. No, we're going from E to D, sorry. And now this time we have our current I2. Now, what we can do is draw out the direction of which the current is going in. So we could see that when we go from E to D, we would be opposing the current. So that tells us that the potential across this 5 ohm resistor, that is going to be positive. So again, opposing the current is positive potential, going with the current is negative. So we have plus the 5 ohms times the current I2. And now for this battery, I should say for batteries, it does not matter the direction of the current. You just have to look at if it's going from positive to negative or from negative to positive. Here we can see that we're going from positive to negative potential. So this is going to be minus 21. So from B to C, then from C to B, we have nothing there. And then from B to A, we have nothing there. So just like that, that's our second equation. Now for our third one, I did say we're going to use the junction rule. So also, sorry, I realized I erased this part. I did not need to erase that. But we are going to be using the junction rule for our third equation. And we're going to be looking at this point B just because it's convenient for the arrows and we could see the current going in versus the current going out. So we could see I3 is going into the point B and I1 is going into the point B as well. So on one side of the equation for our junction rule, we have I3 plus I1. And on the right side, we only have I1 going out. So it would make sense that I2 is going to be equal to the sum of the currents I3 and I1. So on the right side, we just have I2. And just like that, we have our 3 different equations to solve for our different unknowns I1, I2, and I3. Okay, so here I just cleaned up the board. I just put our equations up here. And now at this point, it's just a bunch of algebra to solve for our different unknowns. So notice how for the junction rule equation, we already have I2 in terms of I3 and I1. So that means what we can do is that using the second equation, we can substitute I2 into that equation. So we have 0 is going to be equal to negative 18. I also got rid of the units, so that way it's just less writing. And plus 12I1. And then we have plus 5 times this expression for I2. So we have I3 plus I1. So we have I3 plus I1. Then we have this minus 21. And before we do anything else, what we can do is we have this negative 18 minus 21. So we can combine those. So we have, when we do negative 18 minus 21, that gives us negative 39. So I'm just going to get rid of these and put in the front negative 39. And now we can multiply these two terms right here. So we have negative 39 plus 12I1. Then we have plus 5I3 plus 5I1. Again, we could combine things. We see this plus 12I1 and this plus 5I1. That gives us 17I1. So I'm going to get rid of this one. And now we're left with here 17I1. Now, this is where we use our first equation to get I3 in terms of I1. So getting I1 to the left side as well as this negative 18, when we do that for our first equation, we get left with 18 minus 12I1 is equal to negative 6I3. Dividing both sides by negative 6, we then get on the left side, this 18 is going to turn into a negative 3. And this negative 21I1 is going to turn into a plus 2I1, sorry about that, plus 2I1. And that is going to be I3. So bam. Now we just factor this into this equation right here. So we have negative 39 plus 17I1 plus 5 times this expression right here. So we have negative 3 plus 2I1, bam. And now we just solve for I1 at this, going further. So multiplying these two terms right here, we have negative 39 plus 17I1. Then here we would have negative 15. And here we would have 10 plus 10I1. And again, we combine like terms. So this negative 39 minus 15, that's going to be negative 54. And this 17I1 and this 10I1 is going to turn into 27 plus 27I1. Getting the negative 54 on the left side, we then have 54 is equal to 27I1. And now dividing both sides by 27, we can see that I1 is equal to 2 amps. And just like that, we have our solution for I1. And now at this point, it makes everything a lot more simpler. So here earlier, we had this expression for I3 in terms of I1, substituting in 2 for I1. So we have negative 3 plus 2 times 2 is equal to I3. So we have negative 3 plus 4. Then we see that I3 is going to be equal to 1 amp. And now using the junction rule equation, we can solve for I2. So I2 is just going to be I3, which is just 1 amp, plus I1, which is 2 amps. And from here, we can see I2 is equal to 3 amps. So that's how you could solve for the different unknowns of currents, I1, I2, I3. And this method you could apply to any type of current that you're looking at, so as long as you're following the direction of the current. I think for me, writing out these equations is the hardest part. I think in general, that's probably the hardest part. But as long as you pay attention of where the direction of the current is going, you would be able to get these in no problem. So yeah, hopefully this video will help you out. And yeah, see you guys later.